Welcome, this is lecture number 42. In this lecture, we are going to talk about dynamics of linear time invariant system and vector field with MATLAB demonstration. In this lecture, we want to recapitulate state space model of particularly the part of LTI model of a boost converter, and then part of LTI model of a boost converter, then phase plane geometry using small signal model, then understanding vector field of linear time invariant first order as well as second order system, and then how to draw vector field along with MATLAB demonstration. So, first we will start with an ideal boost converter with AC equivalent circuit, and this is well known. So, this is an ideal boost converter that we have explained multiple times in this lecture, and we have also discussed that how to obtain AC equivalent circuit of an ideal boost converter. And this circuit represents a linear circuit, this particular circuit, the AC equivalent circuit. And what we are going to do, if we want to write the state space model by considering inductor current to be one state and the capacitor voltage to be other state. In this case, the capacitor voltage and the output voltage are same, but in a practical boost converter there can be slight difference because of the ESR. And we are considering the duty ratio perturbation to be input, that means it is the control input, because in state space model we generally write x dot equal to Ax plus Bu. So, the control input here is the duty ratio. So, if we write the equation of the inductor current dynamics, if we write the dynamics equation of the inductor current, then this is a well known equation. This we have referred earlier in the AC equivalent circuit. So, if we write in terms of state space form x1 dot, which is nothing but dIL dt, because we have taken x1 tilde is nothing but inductor current tilde, then we can obtain this model of a boost converter inductor dynamics. We can also write the dynamics of the output voltage like the capacitor voltage, and this equation is also straightforward, and then we can write this x2 dot, where x2 tilde dot is nothing but dV0 dt, here it is a voltage tilde dot. So, we can obtain this equation, and finally the state space equation x1 dot and x2 dot, these are all tilde because these are part of quantity around their steady state quantity. So, we can obtain the overall state space model of the overall part of state space model of the AC equivalent circuit of the boost converter. And this A matrix is a system matrix. So, this is a standard representation of a state space model, where x is the state vector, where we have taken here the inductor current and the output voltage x1 and x2, and u tilde we have taken as the duty ratio, which is a control input, and here we have a supply disturbance, which is a disturbance input, that is why it is coming to be E matrix. Now, if we consider an open loop boost converter, where we are considering the instantaneous duty ratio to be the fixed duty ratio, that means the perturbation in the duty ratio is 0, then the supply disturbance is also considered to be 0 open loop. Okay. So, this is 0, that means this part is shorted, and this part where we had that V0 into d tilde, that is 0 because we have ignored the perturbation of the duty ratio, because we are using a fixed duty ratio. Then we will only have this equation, because we will have u tilde, which is nothing but d tilde equal to 0, and then v in tilde equal to 0. So, we will get x tilde hat equal to a into x tilde. So, this represents x dot equal to Ax, which is nothing but this represents an autonomous system, linear time invariant system, where there is no perturbation in the input signal. Okay. Now, we want to study the dynamics of linear time invariant autonomous system. Okay. So, first we will start with the first order system, where x is the state and it is a first order equation dx dt is a into xt, where a, whether it is positive or negative or it is 0, depending upon that the stability of this system will be determined. So, if we write dx dt and if we take Ax term to the left side, then you can represent this, and this quantity we are representing in terms of Fx, which is equal to 0. Okay. Now, if we solve this first order differential equation, because we have dx dt is equal to a into x, then you will get x of t is nothing but x of 0 into e to the power a into t. This is a standard form, right. So, this is what we have written here. And if you differentiate x dot t, then what you will get? You will get a into x t, and that you can write, because if you write x dot t, it will be a into at into x 0, and this term is already it is written, it is nothing but this term, right. So, we can write. Now, we got x dot equal to this equation. So, we want to draw the state space form, that means x and x dot plane, right. So, in this plane, if we consider initially the a to be negative, okay, then we know that if a to be negative for this system, then this system will be asymptotically stable, because a here acts like an eigenvalue, because it is a first order system. Now, the starting point for this x axis is the x 0. Then if you take x dot and if you obtain what is my x dot t at t equal to 0, you will find it is nothing but what is that? X 0, right, into a, because this x will be x 0. So, it will be like this, quantity will be a into x 0. Since a is negative and x 0 is positive, so this quantity will be negative, right, because we have considered a to be negative and x 0 to be positive. So, there a into x 0 must be negative, and this is coming here. Then as time increases, that means as t increases, what we will find that x of t, which is nothing but x 0 into e to the power a t. Since a is negative, this quantity will decrease, right. So, this quantity will decrease in this direction. What about x dot t? X dot t, if you write, it is simply what we have obtained, a into x 0 into e to the power a t, right. It is simply like this. So, this quantity, since it is already negative, this quantity is negative. So, we can say that e to the power a t, this quantity will decrease. So, naturally this quantity will increase. So, it will go in this direction. So, effectively their combination will move along this line, and this is the direction along which that trajectory, that means this vector will move, and it will finally approach towards origin. As limit t tends to infinity, it will go to 0. That means, if we draw the time domain axis, so this will be like this. So, this is my x 0 and this is my x of t axis. And if we draw x dot t, if we draw x dot t, then what we will find that we have considered it will start from negative and it will slowly approach towards this. So, this is my time axis x dot t, right. So, it will approach to this. Now, if we consider a to be positive, the same thing, then we know what is our x of t. It is again x 0 into e to the power a t. X dot t will be x 0 into a into e to the power a t. Since a is positive, that means as t increases, e to the power a t will increase. And what is the equation of this line? So, this is f x equal to 0, and what is f x that we have chosen? It is nothing but x dot minus a x, that is equal to 0. So, x dot equal to a x. So, it is a straight line with a positive slope because a is positive, and that is exactly that slope is positive here. That means if you start with a point x0 initial condition, then this will be a into x0 since a is positive, and then it will move along this vector and it will go away because it is unstable. So, it will go away from the origin. So, that means if you use a different color, it will go away from origin and the system is unstable, because if we see the time axis, then if we start from this point x0, it will slowly increase like this as time approaches. Okay? And similarly, if we take x dot t with respect to t, then this will, if we take, it will also move along like this. Okay? Now, if we consider two stable system, we have taken one first order system with a negative, that means it is stable system, it is a stable system. We have considered another system, again it is a negative, it is also stable system. It is not necessary that two system has to be stable, one can be stable, other can be unstable, both can be unstable, both can be stable, right. Multiple scenario will happen, but if we understand how to draw the vector field, then we should be able to draw for any condition on A1 and A2, then we can draw the vector field. And we know for the individual vector field, if we start with x1 0, since A1 less than 0, so that means this is my A1 x1 0, so the point will move along this line, this is well known. Similarly, if we take this one, that means this is my A2 x2 0, again this will move along this line and both the cases stable, so they will approach towards origin. Now, if we combine and draw x1 versus x2, here we have drawn x1 versus x1 dot, x2 versus x2 dot. Now, if we draw x1 versus x2, then this component is x1 0, this length, right, this one along this, and this is nothing but our x2 0, right. So, this component is x1 0 and x2 0. So, now it will start and then it will slowly come towards origin, right. So, towards origin. But the question is, how does the path look like? And that path we call as a trajectory. That means, if you start with the initial condition, then for given value of A1 and A2, you will get an unique path along which it will move along towards the origin, since A1 and A2 are negative because the system is stable. And we are interested to draw this vector field, how to draw it. Now, we have considered a second order system and we know the solution of individual subsystem which are first order can be written in this form. Now, we can combine together to create a kind of a vector. So, this is like a state vector where this is my state vector and this are the initial vector, or you can say initial vector, or I can say initial state vector, or simply I can say initial vector, okay, initial vector. And this is now, it looks like a square matrix and it is a decoupled system because each system like a individual subsystem which does not depends on the other, that means they are totally separated. Now, we can write in a compact form, that means this matrix, this particular matrix we are writing again here. Now, we can multiply with an identity matrix, this is an identity matrix. We are multiplying with an identity matrix, identity matrix. Why we are doing that? And this we call vector x, this is a vector. This is also vector x0 which is a initial state vector, and both cases they are combination of two state x1 x2. And this is an identity matrix. Why we have considered that? So, if we write down again, then I am rewriting the equation again. I can consider this to be a column vector. for example, we will see the significance of this column vector. I will consider another column vector to be Vy. So, that means there are two column vector Vx and Vy. Okay? Why I have considered this? Since it is a decoupled system, why I have chosen this column vector? Let us first draw in x1 x2 axis how does the vector look like. So, it is a column vector, and you see if you go back, this is the axis which corresponds to x1 and this is the axis which corresponds to x2. That means, if we draw x1 x2 axis, then we are interested to know what is the component of this, what is the component of this vector along x1 axis, along x2 axis. Similarly, what is the component of this vector along x1 axis, along x2 axis. So, this is why we are interested. So, the first vector has 1 unit component along x1 axis, 0 unit component along x2 axis. So, you can write 1 unit length here. So, this is the vector, this vector looks like this. That means, this Vx vector will be simply like this vector consisting of 1 unit length along x1 axis. Similarly, Vy vector has 1 unit along x2 axis, that is why it will look like this, 1 unit length. Now, we can draw two vector and we want to write that what is my initial state, that we will see soon. Suppose if we want to create a vector using a linear combination of Vx and Vy vector, and you see since it is along x1 axis 1 unit length, this is along x2 axis 1 unit length, we call them as a basis vector. So, these are the basis vectors. The basis vector. So, this basis vector, since we are scaling this vector alpha times, so this alpha time Vx is this and alpha 2 times Vy is this. Why we are choosing? Because their resultant should combine to generate the, this is my initial vector, or in other way, if the initial vector is given, if this is given, because what is this? This is x0 which has two component x1 0 and x2 0. That means, I can say in this axis it has x1 0 unit and in this axis it had x2 0 unit. So, then this is the coordinate and I want to match this coordinate is horizontal and the vertical displacement, and from there I can solve alpha 1 alpha 2. That means, what is the bottom line? The alpha 1 Vx plus alpha 2 Vy is my x0, which is nothing but, from this case it is nothing but x1 0 x2 0 is nothing but alpha 1 0 plus 0 alpha 2, which is simply nothing but alpha 1 alpha 2, because each of these Vx, their magnitude is unit length, right. So, that is why we are writing alpha 1 alpha 2. So, alpha 1 here is simply x1 0, alpha 2 is here nothing but x2 0. So, we can get this column vector any point in x0 axis, that means any point. So, any point x0 in 2-dimensional space, this is a 2-dimensional plane x1 x2 can be connected by spanning this unit basis vector. By spanning this basis vector, we can generate any point in this 2-dimensional plane. Okay? So, what happens if the vector Vx and Vy are not orthogonal? What happens if the Vx and Vy are not linearly independent? So, here they are linearly independent because in the vector diagram, when we will call linearly dependent, when they are parallel or they are basically one is a subset of other, right. But since here Vx and Vy, they have certain angle, they are not overlapped or they are not parallel, so they are linearly independent. Now, the column vector which are not orthogonal, so we can consider another scenario A. where the first vector is Vx 1 1. So, that means you take here 1 unit length here and you take another unit length. So, this is my 1 unit length and this one I have 1 unit length. So, that together they combinedly create this Vx. Similarly, if I take Vy 1 unit length along this axis 1 unit length and along this axis 2 unit length. Okay. So, they combine, if you join them, this is my Vy. Okay. So, you can draw any vector in 2 dimensional plane for any 2 dimensional vector, right. So, we got now for this particular case, these are the basis vector. So, earlier the basis vector was along x1 and x2, but those vectors are orthogonal, but now they are no longer orthogonal. For this case, here the basis vector are Vx and Vy, and we have to represent our initial condition or x0 in 2 dimensional plane using these 2 basis vectors. So, here our basis vectors in this case Vx, Vy, these are the basis vector and they are not orthogonal, right, they are not orthogonal because they have angle, but that angle is not 90 degree in this case. So, the angle is less than 90 degree, but greater than 0. Now, if I again take an initial condition here which has a distance, let us say x1 0 from here and which has a distance x2 0 from here. So, we can resultant vector can be mapped by scaling this alpha 1 Vx, the Vx vector this by alpha 1 spanning, and this vector which was Vy here, it was our Vy, we can span in the negative direction, so that the resultant this plus this will give you this Vx x0. So, we can generate this vector from these 2 vectors. That means, we can in fact any point x0 can be mapped by Vx and Vy by spanning them. That means, they are scaling those vectors and we can obtain the resultant vector. So, again we can x0 can be mapped or connected in this 2 dimensional plane by Vx and Vy by spanning using their coefficient alpha and alpha 2. But this is not possible if 2 vectors are linearly dependent. So, our first requirement, the vector must be linearly independent. Now, we are going a decoupled system, writing again Vx, Vy. So, we can write the solution, that means our original equation x dot. So, for x1 dot we know it was a1x, for x2 dot it was a2x2. So, you can write x dot to be a1 0 0 a2 into x. So, for this system, even for any second order system, arbitrary system, whether it is in this form or other form, if we can find, we have not yet discussed what are the eigenvalues. So, for this case we will consider a1 a2, they are given, and in subsequent, in the next lecture we will see when we will find eigenvalues, then this will be written in terms of e to the power the eigenvalue times t alpha into Vx and alpha 2 into Vy. So, we can solve this system by writing this equation, and this is very standard, well known, a second order system. Even if you have a nth order system, you can write e to the power a1 2 alpha 1 V1, e to the power a2 t alpha 2 V2, and so on. We can add it e to the power an t alpha n Vn. So, you can write n number of combinations. For this second order, at t equal to 0 initial condition, this quantity will be 1, this will be 1. So, it will be alpha 1 Vx plus alpha 2 Vy equals 0, and that we have already drawn, that we can draw this x0 vector by a combination of Vx and Vy by spanning them using scalar quantity alpha and alpha 2. So, this Vx, Vy, the 2 dimensional vector, they are linearly independent and orthogonal. Now, we are considering another case, the coupled system. that we have already discussed that Vx and Vy they are not orthogonal, but again if we have the equation which we have not written yet, suppose we consider the same A1 A2 for the system, but now the vectors are different. We want to see how does the vector look like, and we have already discussed that if this is my x1 axis, Vx Vy we can get x0 by a linear combination. It is also Vx Vy, they are second like a two dimensional vector, linearly independent, but they are not orthogonal. So, now how to draw vector field? So, whatever we have drawn here, we have as if drawn just the initial condition, right. If you take x dot equal to Ax, so we generally get x of t to be e to the power a t into x0. So far we are able to at t equal to 0, we are able to locate, because this is a two dimensional, this is 2 cross 1 two dimensional vector, we are able to locate the initial vector in the two dimensional plane. But we want to see how does this point move if the system is stable, how does this point move in this two dimensional plane, what is the trajectory and how to draw the vector field. So, this trajectory can be drawn by using vector field. That means, every point if you draw a tangent, so you will get the direction of vector field. So, by that computing the direction of vector field, we can slowly move the point and we can eventually draw the trajectory from where that x, like x0 will that will follow that path to reach to origin at limit t tends to infinity for a stable system. So, how to draw the vector field? Let us start x dot equal to Ax, where the Ax can be written like a vector Fx as a function of x, where we are starting with a decoupled system A1 A2. Okay. So, one approach using MATLAB custom simulation and other approach using analytical approach using vector field. So, we will first consider how to draw vector field in MATLAB, because we want to get some visual understanding before we draw the real vector field in the in this like a presentation. So, first I have considered one dynamical system, and what is the dynamical system? X dot equal to Ax, right, and since it is we have taken only two state, you can see x1 and x2. So, this is also 2. So, this has to be 2 cross 2, and that means what is my state vector? It is nothing but x1 and x2. And what is my A matrix? I have taken here, I have taken A11, A12, A21, A22. That means I will get x1 dot x2 dot is equal to A11, A12, A21, A22 into x1, x2, which means x1 dot is equal to A11 x1 plus A12 x2 plus, because there is no input. So, that is it. And what about x2 dot? X2 dot will be A21 x1 plus A22 x2. Now, we already know that how to plug in this equation in MATLAB, because the first thing for x1 we need one integrator, right. So, this is one integrator, and if this side is our x1 dot, then this will be x1. This we have already learned multiple times, right, because we started this presentation in lecture number 4 in the very first week. Then what is my x1 dot? So, it is a combination of A11 x1 and there will be A12 into x2. From where we are getting this x2? Again we will create another one. So, let us draw it here. That means we will take another integrator and this is my x2, and this side will have x2 dot, again this side will get, it will have its own self coefficient which is a22, okay. Then it will also have the other coefficient which is a21, and in this case it is simply this one, right. Then we can connect this one to this point. So, this gives us the complete equivalent, right, and this is exactly what I did. A11 like sorry A11 into this, A21 into this, A12, A22, whatever I have explained. And we already know that if you go inside the integrator, like here we will have x1 dot, it is x1. So, you can set the initial condition x1 initial condition right inside the integrator. If you go click it, we will show it very soon. Now, suppose if we take x dot is equal to ax plus bu, where u is the input. This is a general representation of a state space system, where B matrix is nothing but B1, B2. Then what will be our equation? X1 dot will be X2 dot will be A11, A12, A21, A22, X1, X2 plus B1, B2 into U. So, this is what I have exactly realized. But we are not going to consider input, but this model we made because if we want to use, because in DC-DC converter ultimately we need to incorporate input, right. So, there will be input voltage, gate signal, all this will come, but to start with we can remove the input. So, you see I have not connected any input. So, input term there is no effect, nothing will come. So, then I am, in order to draw vector field, I have just created one .m file which is like a system simulation underscore simulation.m, and it will ask for system parameter, although I am not giving any parameter, but this is used if I want to incorporate a DC-DC converter model. So, for the time being you can ignore this, because in this particular lecture we are not calling this parameter, we are writing all the A1, A11, A12, A21, A22 by numerical value. So, that means we are putting the values, we are not using any symbol. B1, B2 we are B1 I am getting Q 0. So, if Q equal to 0 there is no input, right. So, I am using A matrix and B matrix I told you, and these are the initial condition figure, and then you can plot for the initial figure. Now, if you go for system simulation, it is continuing, because this whole file is length is quite large. I will show you. So, I have broken into multiple lines. Another part I am calling running for 200 milliseconds. So, you can change the time. Now, I am calling something called system underscore dynamic dot xls file. This file consists of this Simulink model. Then I am getting the data from the system result dot time, system result dot data, and I have already explained how to access the data without putting a scope. Then I want to plot them. In the first figure I am taking two sub figure like a subplot, and the first plot is x1, second plot is x2 with respect to time, how they are changing. And second figure I am taking phase plane x1, x2, which I am trying to explain, and along with that I am also putting a vector field. What is the vector field? So, it is a quiver plot. That means, if you take, let us say, suppose I want to draw a vector field along x1 and x2. So, this is my x1 axis, x2 axis. Now, I want to plot the vector field by some limit. That means, this is my x1 minimum, this is my x1 max, then this is my x2 max, and this is my x2 min. Now, I want to create a grid. I want to create a grid with this. So, I want to take 1, 2, 3, 4, 5, 6 point. 1, 2, 3, 4, 5, 6 point. So, this number of point 1, 2, 3, 4, 5, 6. So, this is where is the number. So, if I give 100, that means 100 such point along the x axis, and the same number of points should be taken along the y axis. So, it will create a matrix like 100 cross 100, 100 cross 100 dot, and for each it looks like a point in the phase plane where we want to draw the vector field. That means, we are interested to draw the vector field, the direction of vector field. How does it look like, whether it will look like. So, I am just drawing some arbitrary vector field, right. So, it is like a magnetic lines of force, something like that, right. So, that means this part is the lower limit for the x axis, lower limit for the y axis. Then you have to create the delta x, that means difference between these 2 points is my delta x, the x diff, and difference between y point is my delta y. So, y diff, then the figure, and this is a mesh grid where we are creating this dot 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 dot. Mesh grid is creating dot. Then you have to plug in the actual dynamical equation here, which you have already considered, and then it will draw the quiver plot. That means, the quiver plot means this arrow marks, it will plot automatically by computing their direction field, because that if you start any initial condition at this point, suppose if you start any initial condition, then the trajectory will start moving along this direction for short duration. Again you take a point, because even if you draw one point, it does not mean that trajectory will move along this line. So, trajectory direction will keep on changing. So, you have to take multiple points nearby to get more accurate trajectory information. So, let us go to the MATLAB and see how does it work. So, this is exactly what I have presented, the whole plot, and if we open this model, again if we go inside, we can plug in the initial condition here and we can plug in the initial condition here, and this part we have already discussed the methodology. Now, I am running. So, initially I am plotting for A1 1000. So, let us take, if I run this particular part, okay. So, I am running and I am finding what is my A matrix. So, A matrix I have taken minus 1000, minus 2000. So, that means it is like a two decoupled system, and you can check what is my B matrix. So, B matrix 0 0. So, there is no input effect. So, we can imagine that A matrix has two diagonal term, one minus 1000, another minus 2000. So, minus 1000 you can think of A1, that means A1, and minus 2000 like A2. So, A1, A2 both are negative. So, it is stable. Now, we want to draw the vector field. Let us see how does it look like. So, I want to run this program, and this is the initial point. I start with minus 2 and 2, and let us see how does it move. So, if you go, you see I have taken 100 grid. So, let us reduce the number of grid because there are too many grid. So, if I make, let us say initially to understand, okay. So, to understand this point, I am first running with 10 point grid point, that means number of grids are less. So, you will see if you, these are the vector fields. So, if you start from this point, the trajectory will start moving, but it does not mean that throughout this path trajectory direction will remain same, because it may keep on changing. Because if you see here, the trajectory is slowly curving towards this origin, and it is slowly try to reach origin, because this is a 0 0 point. So, it start from here and slowly coming, and this direction field. So, suppose I want to make the direction field. So, I make from minus 15 to plus 15, let us make for minus 5 to plus 5. So, if I go here and if I change the vector field like a minus 5 to plus 5, and now again I want to draw again and want to see how does the trajectory look like in this plane. So, you see initially we have a starting point. You see, if you check carefully, if you draw this trajectory, it is starting from this point, and this point they are moving along the same line, because this blue line indicate the derivative of the vector field or the tangent to the vector field along which the trajectory will move. but after some time, I mean once it passes, then it is slowly deviating. That means in order to plot better, you need to take more points. So, if we increase the number of points, let us say instead of 10, let us say we make 20 and see whether we can get a better representation of the vector field or not. So, you see we have taken a nearby, but not exactly on the same path. So, it is slowly, that means if you could have taken here, so you will get a better representative. So, we can take maybe 50. So, because we are increasing the grid point, so we are taking more and more vector, that means point to draw the vector field. So, this can give you a better representative of the vector field. So, if you go there, that means you see this point started at the same, and if you take this particular path, so we are taking nearby, so it is showing the direction of vector field. That means even if we take the vector field here, so this close by vector field will be almost nearly parallel. Okay. That means this is how it shows the trajectory of the vector field. Now we can check with multiple points. That means we can check with now let us say 100,000 and we can give minus 1000. So let us see how does it look like. I want to show an interesting point, and how does it look like. So this is another point I want to show. Now trajectory is curving towards this, right. So it is actually changing and it is curving, and you see here you will get some overshoot undershoot, because it will have like it is crossing this point for some time, crossing this point, and it might also cross a little bit. So that means some overshoot undershoot effect will be there. But if we could take the earlier one, then there will be no overshoot undershoot, because the earlier was a decoupled system, now we are talking about a coupled system. So if you draw the earlier one, it is like there is no overshoot undershoot, it is like exponentially decaying function. So this is decaying, right. So this is decaying function, right. So we understood how to draw vector field. Now we want to see, can we imagine how does the vector field look like. So we started with this point x fx, and again we consider that vx and vy are the two basis vector, right. So we can write, because this is an identity matrix, this is like our identity matrix, and this basis vector Vx has a dimension of 2 cross 1, this also dimension of 2 cross 1. So now I can write for this particular case A1 Vx, A2 Vx, right. Now I want to draw the vector field. So I told you, in order to draw the vector field, so fx function, this is Vx is the basis vector with the scaling factor of A1, Vy is the basis vector with the scaling factor of A2, and x is the point where we are trying to draw the vector field. So you need to specify the point where we want to draw the tangent. Suppose you want to draw a tangent here, whether it will come towards this, which you have shown in the MATLAB, or where it will go towards this. So that can be analyzed by drawing this vector field. So let us first draw for f1x, it is nothing but a1 vx. So this is my vx and a1 vx is this one. Now we are going for f1x and f2x. That means first this is my f1x that we have already discussed, and the other one is f2x, which is a2 time vy. Then what we have to obtain? We are trying to find the vector field at x equal to x0. So it has this f1x, f2x we have drawn, and x0 that is given. That means it has x10 and x20. That means we are talking about this point. This is x10 component and this is x20 component, right? So that means fx0 can be written as, which is represented by this, can be written as f1x vector into a scaling factor this, f2x vector scaling factor of this. That means I am writing this vector to be my f1x into x10, and I am writing this vector to be I am talking about this vector to be f2x into x20, and their resultant vector is the one which is this one, which is the vector computed at this point. That means this is the direction of the vector. But remember, we need to draw the vector field here because we wanted to find the direction of vector field at this point. So ultimately we got the vector field direction. So this vector field will be parallel to this. That means whatever we obtain, it is the parallel field, right? Because we first draw the vector and then, because it is a parallel vector, right? Because we want to find the vector field at this point. Similarly, we can, if we want to find the vector field at this point, we need to know what is this point location, as if this location is computed after trajectory moves towards, after time t1 interval, and you got x1 on x12 component, because this one is my x11 and that means this is my x11 comma x12 component. So then we can get this vector is nothing but f1x into x11, f2x into x21, and again we need to draw parallel line to this because this is we are computing at this point, right. So by that way we can draw the vector field. Now this vector field example we have set Vx and Vy are the basis vector and we know how to draw the initial condition. What happens if you take x0 in either on this basis vector or on this basis vector? So if you take x0 on that basis vector, you will find alpha, that means our original equation was alpha n Vx plus alpha 2 Vy equal to x0. Since we have chosen x0 along this Vx axis, so alpha 2 must be 0 in this case. That means you will only have alpha 1 Vx equal to x0. So your xt will be simply e to the power this term because alpha 2 is 0. And if you differentiate, you will get x dot equal to a1x. That means the trajectory if we take, it will continue to remain on this line. That means if we choose any point, starting point here, it will remain here provided that your a1 is less than 0. So it will, because the derivative of this vector is on the line, that means the point will move, the vector field direction will be along this line. Since a1 is negative, it is towards this side, left side, right to left. So the point will slowly move towards the origin. So it is called invariant vector field, because if you start the initial condition on that line of the vector, the point will move along the line, it will not go out of the line. So it will be along the vector. This is an invariant vector field, and we will see this will actually lead to what is our concept of eigenvector, okay. But we are not talking here now. Now if you take a couple system, we have taken two vector, right. Then for this again, if we take any initial condition on this, any of these vectors, suppose we took the initial condition, let us say here, then if a1 is less than 0, again this point will move along this line, it will not come out of this line and it will slowly approach towards origin, and this is my vector direction Vx, right. Again it is an invariant vector field. So whether the basis vector, these are the basis vector, whether they are orthogonal or not, but they must be linearly independent, and if you choose any initial condition on any of these basis vector along that line, then it will remain on the line, whether it will come towards origin or go away depending upon the stability property, but it will be on the line, and this is the invariant vector field. So if we compare the first case, this is the vector orthogonal, but they are not orthogonal, right. So these are the two diagram that we set. Then we can map any x0 using this basis vector for system 2 as well as system 1, and then we want to combine like xt and let us say it is zt. Suppose we applied, so this is something like that. Suppose we take an image, this image like this. Suppose you take an image, the image is a circle, right, and this is a plane x1 x2 plane, x1 x2 plane, and we are looking from vertically from like our viewpoint is from the 3-dimensional, it is like along the z axis we are looking at. So, it will look like a circle, but now suppose we have changed the angle, suppose we are looking from an inclination, then the axis may appear slightly different, the axis may appear slightly different and it may appear something like this, and that we call it as a z1 z2 because we are looking from some angle, and then you will find this particular ball will look like an ellipse, right, because bended, because we are looking from another angle. So, when you look from vertically it will look like a circle, but if you look from an angle it will look like an ellipse, right. So, that axis, so this is exactly what z. So, I can take z to be combination of z1 z2, which is an image version by either moving the image, keeping the eye position same, by changing the angle of this plane, or by changing our eye angle itself. So, in each cases as if we are kind of by movement we are making some image processing or some image transformation. From here, so you are multiplying a operator m which is changing the image direction, either your view direction. So, it is ultimately the relative position, I mean it does not, it does not matter, because if both the image plane as and the vision plane they change together, they change and they still appear like a vertical, then there is no problem. But suppose if one of them related to the other changes, then as if we are making like an operator m, where x was our original one and the z is the 1 by operator plane, and if you multiply then this will resemble like this kind of thing where Vx1 and Vy1. So, here Vx1 is nothing but operator into the previous basis vector. So, this is a change in the basis vector by means of the projection, and Vy1 is m times Vy, again operator, same operator. So, it's actually change the angle. So, system 1, system 2 operator. So, if we write Vx1 m Vx, Vy1 m Vy, so if you combine Vx1 Vx2 m into Vx, so it is identity matrix. So, it turns out this operator which is a square matrix consists of Vx1 and Vx2 which is the inclined angle, right, their basis vector. So, ultimately this is, and you will find soon that this is nothing but these are the eigenvector of this system which we are going to deal with. So, what is the system transformation? That means this image processing is changing angle by means of an operator z equal to m times x, or you can write x equal to m inverse z, and this inverse exists because we have chosen m which consists of two vectors Vx1 and Vy1, and both the vectors are linearly independent. As a result, m must be, m will be invertible because the rank will be full rank, because it consists of two vectors, two-dimensional vector which are linearly independent. So, M is a full rank matrix, square matrix. Then if we obtain x dot t, it is the representation of the autonomous system for system 1, and if you obtain z dot t, you will get a couple, and there because of the transformation, so your couple system here is nothing but m times m decouple system into m inverse. So, this is the image transformation has changed the system matrix, okay, and if you decouple one, you will get, that means this combination. Now, since you have not put any value here, so we will see, and we want to see what will happen for this particular case. So, suppose we have taken a1 to be minus 2 minus 3 and the couple system will be minus 1 minus 1. So, we want to see the vector field in decouple system. So, this is my decouple matrix and this is my couple matrix. So, whatever we discussed now, we want to see what happens in this case. So, let us go to the MATLAB simulation. Here we are considering minus 2 0 0. So, suppose let us run this and I will show you that if we run it A matrix and B matrix. So, what is our A matrix? Minus 2 minus 3, and what is my B matrix? 0. So, if I run it, then I will show you So, this is a vector field, and you can see if you choose any vector, that means if I choose an initial condition, let us say on this axis, that means I am choosing let us say 5 here, 0 here. So, my initial condition will be along the axis, yes. So, you see it is along the axis, so it will always go towards this, and this is an invariant vector field that I have told, it will move along this path. Similarly, if I choose the initial condition 0 and 5, so you will see it will move along the vertical axis, yes. Okay. Now, what will happen if we consider this -1, 2, -4, it is -2, -3 we have already considered. So, let us say -1, -1, 2, -4. So, -1, -1, 2, -4. Let me cross check, cross check -1, -2, -4, okay, fine. Now, we want to run it and see. Now, it will no longer even you take vertically, because now the direction field has changed. Okay. So, we cannot expect that it will come, because you can see earlier the basis vector was different, now the basis vector is no longer here, right. So, that means our eigenvector has changed. Okay. So, the trajectory movement got changed, because we have scaled down, it is no longer earlier vertical axis was my invariant vector field, but it is not the case now, right. Similarly, if I choose the same like along this 5 and 0, so it will not run along this path, okay, it will not run along this path, because that direction has changed. But nevertheless, we can always draw vector field and which will show the direction field, right. So, we can do, okay. So, that means the coupled system. So, we need to understand the eigenvalues and eigenvector, and that we are going to discuss in the next lecture. So, in summary, we have recapitulated state space model of part of as well as part of LTI model of a boost converter. We have shown the phase plane geometry using small signal model, but switch model we have not considered here, that we are going to consider next. Understanding vector field for first and second order system, then drawing vector field with MATLAB demonstration. So, with this I want to finish it here. Thank you very much.